So, going back to the Bell Labs was really the golden area of research. And in the U.S., there were several laboratories. General Electric had some labs in a town called Schenectady in the state of New York. Those labs were also very good. I mean, they really had a lot of major developments. IBM, they had this tradition of doing basic research. But probably the best case was the case of the Bell Labs. General Motors had the same. GM was in the business of making cars, but they had a central research facility where they did a lot of basic research. But in the case of the Bell Labs, it's just incredible. It's hard to understand how these people came up with so much stuff. And some of these things were applied. The Bell Labs are gone. And it's very sad. Back in it was, I think, in the 1970s, the courts, the Department of Justice in the U.S. broke the monopoly. So when they broke the monopoly, Bell Labs broke down into many, they were called the little bells. So it was Southwest Bell, Southeast Bell, and then the Bell Labs were bought by somebody else. In fact, they still exist. They have a different name, but they are doing nowhere close to what they were doing before. It's a real shame. And obviously, that's part of capitalism. In the past, when they had the monopoly, the government gave them an opportunity to have the monopoly in exchange for all this development that they could share with everybody else. Nowadays, the company says, well, if we are making $10 for profit, we're going to give it to the investors, and we may not worry too much about research and development. They may take $1 for research and development, and they will just do it for very specific things that they may be interested in. So it's a real shame that happened. There is a fellow who got a Nobel Prize. His name is Stephen Chu. I don't know if you know Stephen Chu. Stephen Chu, he was the Secretary of Energy in the U.S. when President Obama first became president. So Stephen Chu was the Secretary of the Department of Energy between 2009 and 2014. So when he became Secretary of Energy, one of his goals was to change the energy industry in the U.S. And obviously, President Obama was in sync with Chu. So they made major investments in solar. They made major investments in wind. They made major investments in basic science. I mean, Chu was really, and he had his Bell Labs mentality. And one thing that they did in the United States, they created something called innovation hubs. So a hub is a place where you bring a lot of things together, okay? That's a hub. So Chu created the innovation hubs in the US. So the idea of the hub was that he wanted to replicate what they had at the Bell Labs. And he wanted to do this at the national level. So they created a hub to develop the next battery for transportation. And that hub still exists. It's still at the Argonne National Lab just outside Chicago. And it's a $25 million a year project for 5 years. And it brings together people from universities, national labs, and industry. And they work together for 5 years. And the only thing they think about are batteries. How can we make a battery? Remember what we talked about batteries on Monday? You want a battery that will give you 500 or 300 miles per charge. There were 5 things about batteries: safety, energy density, power density, durability, and cost. So the hub is focused on those 5 things. You want a battery that will be very cheap, it will last a long time, store a lot of energy, can be charged in a short period of time, and it will give you a long driving range. So that's the whole idea of the innovation hub. And when these hubs were established, Stephen Chu had the idea of the Bell Labs. In the Bell Labs, everybody came and worked together. They have another innovation hub on nuclear, the next generation of nuclear power plants. Can we bring together people doing modeling and physics and hydraulics and materials, bring them all together to design the next generation of power plants? So that's going. There's one on building technologies. Buildings utilize a lot of energy. So the idea of this hub is to develop better windows, better insulation, better lighting. So that's the focus of the hub. So this is the closest that we have come to recreate what we had with the Bell Labs. And it's a shame. But if you read the history of the Bell Labs, people got Nobel Prizes. When they were hired, they told you, do whatever you want. just come back with results. And they said, okay, I want to buy a laser, and I want to buy this and that. And then Chu, for example, Chu got the Nobel Prize because he was able to cool down single atoms to 0.00001 Kelvin. And by freezing down atoms, he was able to uncover some very interesting behavior of matter at ultra low temperatures. And he did that with lasers, so he got the Nobel Prize for that. And he tells you the story. He got there, he was hired. There were a lot of people walking around. He was free to talk to anybody. Money was not an issue. So it's too sad that went away. But in fact, the first photo cells came from Bell Labs, and those photo cells were used in a satellite. There's a very famous satellite. It was a weather satellite, and it's all covered with photo cells, and those were developed by the Bell Labs. So let's run this video. This is about 10 minutes. A lot of the things that we talk about are going to be discussed here. So I hope that as the person describes this, that all these things will become clear.
The intensity of the light is greatest in the visible portion of the spectrum, and the warmth we feel on a sunny day is due to the absorption of infrared radiation. That warmth is energy. Conventional solar power uses that energy to heat water. The solar cells we will be discussing here convert that energy directly into electrical energy. It doesn't have to be a hot day. All we need is light. A clue to how they do this can be found by looking at the spectrum. A close look at the spectrum produced by the sun reveals thin darkened lines in the rainbow of the visible colors. These darkened lines are caused by atoms in the sun's and the Earth's atmosphere absorbing precise energies of light. These patterns of lines, like fingerprints, are called absorption spectra. The understanding of how atoms absorb and emit light reveals secrets of the electronic structure of the atom and is crucial for our discussion of the modern silicon solar cell. Niels Bohr proposed the first successful model of the hydrogen atom in 1913. It was a simple planetary model like the Earth orbiting around the sun. A light negative electron in a circular orbit around a heavy, nearly stationary positive proton. Instead of a gravitational force, an attractive electric force holds the electron in its orbit. In order for the model to work, Bohr had to make a radical proposal. The electron can only occupy certain stable orbits with prescribed energies. The electron orbit closest to the proton has the lowest energy. Energy is needed to pull or lift the electron away from the proton, so orbits with larger radii have higher energies. If an electron is to jump from a lower orbit to a higher orbit, it will require an energy source. The energy source? Light. The electron can absorb a photon of light and use all of that photon's energy to jump from a lower energy orbit up to a higher energy orbit. Conversely, when the electron falls, it will emit all of its extra energy as a corresponding photon of light. It is simply conservation of energy. The energy of the photon is completely absorbed by the electron, allowing it to jump to the next energy level. Only particular photons can give their energy to the electron. That photon's energy must exactly match the energy required for the electron to jump. You may remember that there is an inverse relationship between energy and wavelength. So we say that the electron absorbs a particular wavelength or color of light in order to gain the energy required to jump energy levels. Let's look at an example. Say that the electron is in the second energy orbit. It can absorb the energy of a red photon and jump to the third energy orbit. When it falls back to the second level again, it must emit a red photon such that the total amount of energy remains the same. Similarly, an incoming blue photon will excite the electron into the fourth energy orbit. If the electron falls back, it will emit a blue photon, and so on. The result? The hydrogen atom can absorb photons of light with particular wavelengths, or energy, and it can also emit photons of light with those same particular wavelengths. So for an excited hydrogen atom, we would expect to see particular wavelengths of light produced as the electron falls back and emits photons of light corresponding to those energies. This emission spectra of hydrogen is exactly what we see. Notice that only particular wavelengths of light are emitted, wavelengths that correspond to the required amount of energy to jump between levels. Furthermore, Bohr was able to calculate the exact wavelengths of the spectral lines of hydrogen in the visible region of the electromagnetic spectrum. What does this have to do with the sun? The dark lines we have seen in the sun's spectra are direct evidence that hydrogen atoms are absorbing energy from the sunlight. Why? Because they match, line for line, the emission spectra of hydrogen produced in the laboratory. These spectral lines become a valuable tool that we can use to learn about the electronic structure of the atom. However, while Bohr's model was extremely successful of predicting the wavelengths of light in the spectra of hydrogen, it failed to predict the light spectra in an atom with more than one electron. That success would have to wait for the birth of quantum mechanics. The first papers that described quantum mechanics were published in 1926. They not only gave us a description of the atom when more than one electron is involved, they completely revolutionized physics and chemistry. The atoms of elements, other than hydrogen, contain 2 or more positive protons and an equal number of negative electrons. The number of protons identifies the element. You may recall that the positive protons are located at the compact center of the atom called the nucleus. Also in the nucleus are the electrically neutral particles called neutrons that will not enter into our discussion here. The electrons can be thought of as filling diffuse shells that surround the nucleus, similar to the orbits of the Bohr atom. The first shell can hold up to 2 electrons. The second and third shells can each hold up to 8, and so on. The modern photovoltaic cell consists primarily of silicon atoms. An atom of silicon has 14 protons. Of its 14 electrons, 2 fill the first shell, 8 fill the second shell, leaving 4 in the third shell. These 4 outer electrons are called valence electrons. They are important because they are involved in interactions with other atoms, as in the case of chemical bonds. But ordinary silicon will not help us capture and use the energy of the photons coming from the sun. We will need 2 other elements that are close in their electronic structure to silicon. The first is boron. An atom of boron has 5 protons and 5 electrons. 2 filling the first shell, leaving 3 valence electrons in the outer second shell, 1 less than silicon. The second is phosphorus. An atom of phosphorus has 15 protons and 15 electrons, with 5 of these valence electrons, 1 more than silicon. If we bring 2 atoms close together, the valence electrons from each atom will be attracted to the positive nucleus of the other atom. Pairs of valence electrons get shared between the atoms, 1 from each atom. This is the basic idea of a covalent molecular bond. Molecules are often represented with ball and stick models. The balls represent the atoms, and the sticks represent the bonds formed between their valence electrons. Molecular bonds not only hold atoms together to form molecules, but they are also responsible for holding atoms together in a covalent crystal. An example of a covalent crystal is a crystal of carbon. It has 4 valence electrons and crystallizes in a tetrahedral pattern, forming a beautiful gem, the diamond. Silicon, too, has 4 valence electrons. In a silicon crystal, each atom bonds with 4 neighboring atoms in a tetrahedral pattern. True, the silicon cell may not be a beautiful thing, but a crystal of silicon forms the jewel of modern electronics and our photovoltaic cell. For our discussion, we will simplify the representation of the silicon crystal. We represent the 3-dimensional crystal flattened to 2 dimensions. Each silicon atom, with its 4 valence electrons shown, is bonded to 4 other atoms. If we view our flat crystal along the edge, we see what appears to be a simple row of silicon atoms. Pairs of valence electrons form the covalent bonds between the atoms. Collectively, they form the valence band. Unoccupied atomic orbits with higher energy merge to form the conduction band. These 2 bands are separated in energy, much like the regions between the allowed orbits in the Bohr model of the atom. This energy difference is called the band gap and refers to an energy interval where no electron is stable. Since the silicon atoms in the crystal are electrically neutral, we will indicate this neutrality by graying them out. Now, let's shine a light on our silicon crystal. If the incoming photon's energy is insufficient, the electron will stay in the valence band. However, if a photon of light has sufficient energy, a valence electron can absorb that photon, jumping up into the conduction band. It just so happens that such photons are abundant in sunlight. When sunlight strikes the silicon crystal, the photons are absorbed by the valence electrons, promoting them to the higher energy conduction band. Why do we want electrons in the conduction band? If electrons are in the conduction band, they are free to move and therefore can carry an electric current. Now, because the region the electron left behind, was originally electrically neutral, the loss of the negative electron leaves this region positive. The positive region is called a hole. We will color it red for its net positive charge. Remember, electrons are colored blue here to designate their negative charge. Note that the crystal is still overall electrically neutral with the same number of positive charges and negative charges. However, electrons, once promoted, can spontaneously fall back into the hole in a process called recombination. If we are to use the energy of the electrons, now promoted into the conduction band, to power our electrical devices, we must first separate the electrons from the holes before they can recombine. We can accomplish this with an electric field. A simple example of this would be connecting a battery across the ends, say a positive terminal on the left and a negative terminal on the right. The positive terminal will attract the mobile conduction electrons so that they will move toward the positive side. At the same time, valence electrons move to fill the holes, leaving new holes behind. The result is that the holes migrate toward the negative terminal, and we have an electric current. But a crucial point for our solar cell is that we don't need a battery to create our electric field. A modern solar cell incorporates an intrinsic electric field that will separate our charges, giving us the current we need. So how do we create this electric field? A modern solar cell uses a p-n junction. Look again at our flattened, electrically neutral silicon crystal. We again show this neutrality by graying it out. Doping is a process where small numbers of impurity atoms replace some of the silicon atoms in the crystal. One can make N-type silicon by adding impurities, such as phosphorus with 5 valence electrons, one more than silicon. When in the crystal, 4 of its valence electrons form complete bonds with neighboring silicon atoms. This leaves one extra valence electron that will orbit the phosphorus in a Bohr-like orbit at very low temperatures, but will diffuse through the crystal at ordinary temperatures. A phosphorus atom is called an electron donor because it donates an extra electron to the silicon crystal. Because the phosphorus atom has one more proton than silicon, it has a net positive charge. We will color it red to denote this extra positive charge. One can make p-type silicon by adding impurities, such as boron, with only 3 valence electrons. It forms only 3 complete bonds with the neighboring silicon atoms, leaving one incomplete. This incomplete bond has the ability to capture an electron, usually a nearby electron from the valence band. This neighboring electron leaves behind a positive hole that can diffuse through the crystal at ordinary temperatures. With an extra electron near the boron, the region has a net negative charge. Because of this, the boron is called an electron acceptor. We will color the boron atom blue to denote its net negative charge. A p-type and an n-type silicon in contact with one another form what is called a p-n junction. Electrons from the n side diffuse across the p-n junction to the p side, and holes from the p side diffuse across the p-n junction to the n side. The electrons and holes can then recombine. The result is a net negative charge on the p side of the junction and a net positive charge on the n side strong electric field across the junction. Now, when we shine light at our p-n junction, an electron will be excited from the valence band into the conduction band, leaving behind a hole. This time, however, before the hole and electron can recombine to emit a photon, they are separated by the electric field created by the p-n junction. The negative electrons move to the positive region, and the positive holes migrate to the negative region. By separating the electrons from their holes, we have prevented their spontaneous recombination and loss of their excitation energy. Now we have all of the pieces required to construct our silicon solar cell. We start with a metallic layer, which serves as an electrical contact and as a substrate to support the rest of the cell. A thin wafer of boron-doped p-type silicon is laid down. Phosphorus is then diffused into the top surface, forming a p-n junction very near the top. With the p-n junction near the top, most of the sunlight will easily reach the junction. An anti-reflective coating is sprayed on the front surface to cut down on lost reflected light. Finally, front surface contacts are made to collect the electrons arriving from the junction. This grid is constructed with as few contacts as possible so that the p-n junction isn't shadowed too much. We can now power a light bulb or electric motor by completing the circuit. Our cell is complete. Photons of sunlight pass through the thin N layer. In the junction, their energy can be absorbed by electrons and excited into the conduction band, leaving behind positive holes. But before these can recombine, the electric field in the p-n junction separates them. The electrons move toward the front surface, and the holes move toward the back. Then they travel through the load and around to the bottom of the solar cell. The number of electrons that leave through the front contact is equal to the number of electrons that return to the back contact where they recombine with the holes. As more photons of sunlight are absorbed, electrons are excited into the conduction band, and the process is repeated. No electrons are used up in the process. Photons give up their energy to create electron-hole pairs. The electrons give up their energy in the form of electrical power and return to the back contact of the cell where they finally recombine with the positive holes. It is simply conservation of energy, and the silicon solar cell should work in principle indefinitely. With no mechanical parts to break down, solar cells have operated in practice for 25 years or more.
Okay. Questions? Was that easy? Was that clear?
Normally people do N-type region much longer for silicon. Because here they show P-type was doped by phosphorus.
Yeah, and I'm going to show some examples here in a minute of the different types of solar cells. We'll see this in a minute. And obviously, everything depends on the materials. I'm going to show you some cases with copper, indium, selenite, for example. Then the dimensions are going to be different. But you know, how do we decide? How do we decide what would be a good photovoltaic material? I mean, we know silicon works, and that's been around for a long time. I mean, if you were working for a company and your boss told you, please tell me which photovoltaic material should we investigate? How do you decide what materials to investigate? I mean, how will you do it? Search. Okay. So what do we search? What do we search for? Very good. So we can look at absorption, number one. Yeah, what else? Performance. Carrier mobility, how well the electrons can move around. Now, do we have to go to the laboratory to do all those measurements? Do we have to go to the laboratory to do those measurements? You know, doing experiments can take a lot of time and a lot of money. Yeah, you know, and in the old days, you know, we had to go, that's what we call, have you heard about Edison? Thomas Edison? In English, we have an expression called Edisonian. If you go to the laboratory to try many things, you are doing science like Edison. So Edison had, I don't know how many patents, you know, hundreds of patents, but one of the most famous one was the incandescent lamp. And we were making joke about the incandescent lamps on Monday, if you remember. But Edison, you know, he came up with tungsten as being a very good filament for incandescent lamps. But before he tried tungsten, he tried every material available. He tried carbon, he tried silver, he tried platinum, he tried copper, he tried aluminum. I mean, he went through the periodic table and he tried everything, and then at the end, he said, oh, tungsten works really well. And he spent a lot of time, you know, trying different things. That's what we call Edisonian approach. The time of Edisonian research is gone. You know, it just takes a lot of time and a lot of money to go to the lab to try many things. This is why we have supercomputers now, okay? So what we have, instead of having somebody in the chemistry lab mixing things, we have somebody on a keyboard solving Schrödinger's equation. It really boils down to that, okay? And there is something called there is an approach. You probably have heard about this. It's called DFT. Density functional theory. Have you heard about that? Okay. This is an approach to solve Schrödinger's equation with DFT. And there are codes. In fact, a group in Vienna, in Austria, they developed one of the most powerful codes to solve Schrödinger's equation through DFT. So what people do now is they do DFT calculations. And they start looking for materials. The nice thing about it is that if your calculations are good, everything that you mentioned, absorption, mobility, we talk about properties, can be calculated, including the band gap, which is very important. You can get very good estimates of the band gap. And why is the band gap important? Because you have to match certain frequencies of the spectrum. If your material has a band gap that is far away from the visible parts of the spectrum, you don't even waste time. You want a material that has a band gap value that's going to match the radiation from the sun, okay? And you can predict it. That's the nice thing about quantum mechanics. You can predict all those properties. So that's what we do. All these new generation of materials are being identified by doing calculations, by solving Schrödinger's equation, okay? That's how we do research today. It's just brute computing power, solving it, and then looking at different compounds in different materials. Now, in this case, you know, silicon, look at phosphorus, look at boron. These are very simple dopings. But in principle, you could dope a lot of many other materials. And the question is, how are they going to behave? Now, you can go to the lab and try to mix them to see what happens, but it's going to take you a lot of time and a lot of money. This is where calculations really come into the picture. You do the calculation, and you can predict what the behavior is going to be if you dope it with this material or that material. That's the power of computers and physics today. You know, that's how research is really being done. And every major organization now needs to have access to supercomputers. This is why all universities and research centers are pushing hard either to buy supercomputers or to have access to supercomputers, because you can do this type of calculations to come up with these materials. Any questions? Is that clear? Remember, it's all about quantum mechanics. It's all about these